the James Webb Space Telescope has just made a discovery that has shaken the entire foundation of cosmology. Physicists state that this discovery could completely change our understanding of the universe and discredit decades of scientific progress we have made so far. So, what is this incredible new discovery, and what impact will it have on our understanding of space? Let's find out. The new discovery. The initial observations of dark matter by the James Webb Space Telescope have introduced intriguing findings that may revolutionize our understanding of the cosmos.
Dark, not as in night, dark as in doesn't interact with light, and dark as in we don't really understand it.
These observations have raised questions about our comprehension of both dark matter and the formation of the universe on a large scale. Dark matter, a cosmic enigma, constitutes 27% of the observable universe according to our leading cosmological models. Although it remains imperceptible, its presence becomes apparent through its influence on surrounding baryonic matter. The true essence of dark matter remains one of the most profound mysteries in the field of cosmology. The prevailing cosmological model, known as the Lambda Cold Dark Matter, LCDM model, makes a pivotal prediction concerning the role of cold dark matter in shaping the expansive structures observable in the present universe. Until now, technological constraints hindered the testing of this critical prediction. However, the advent of the James Webb Space Telescope has ushered in a new era, allowing a glimpse into the first billion years of the universe, an era that had remained unexplored until now. The early release science program of Webb unveiled super-early galaxies, offering a unique opportunity to scrutinize the LCDM model's predictions. The outcomes of these investigations defied expectations. The primordial galaxies uncovered by Webb present a puzzle. What insights do they offer? What revelations emerged from Webb's inaugural dark matter observations? Most significantly, how might these results reshape the trajectory of cosmological inquiry? The farthest galaxies uncovered by the James Webb Space Telescope have defied our expectations in several key aspects. Three crucial characteristics distinguish these primordial galaxies, shedding light on the early stages of cosmic evolution. Firstly, these galaxies exhibit a remarkably high redshift, surpassing 11. This indicates that they are super-early galaxies that likely originated within the initial 500 million years following the Big Bang. Secondly, these galaxies possess a substantial stellar mass.
And that may have allowed our galaxy to form. The gravity from this huge construct brought regular matter in to form the Milky Way in the middle.
Approximately on the scale of 1 billion solar masses. This poses a perplexing question because, based on our current models, galaxy formation typically spans about 1 billion years. The observation prompts us to consider whether these might be clusters of proto-galaxies progressing toward the formation of larger galaxies. The unexpected presence of fully developed galaxies within the first few hundred million years after the Big Bang challenges existing assumptions. Lastly, the rate of star formation in these galaxies surpasses expectations for the early universe. This raises the critical question of what mechanisms are driving such heightened star formation activity in these ancient galactic entities. The LCDM model, which outlines the process of galaxy formation, emphasizes the crucial role played by cold dark matter. Various forms identified. Dark matter, a theoretical component of the cosmos, is conjectured to exist in various forms, classified as cold, warm, and hot. These distinctions are based on the velocities at which the dark matter particles move, presenting unique implications for their role in the formation of large-scale cosmic structures. Hot dark matter comprises light particles hurtling at ultra-relativistic speeds. This rapid movement tends to smooth out structures, rendering it less effective in facilitating the aggregation of matter for the formation of galaxies. Conversely, cold dark matter consists of ponderous particles moving at slow and negligible speeds, making it a proficient builder of clumps. Its gradual pace allows for the merging of matter, forming gravitational wells that contribute to the construction of galaxies. Warm dark matter falls between these extremes, with particles possessing intermediate mass and velocity. While it also plays a role in galaxy formation, its lighter particles lead to distinct structural outcomes. The success of the most prominent cosmological model, the Lambda Cold Dark Matter model, hinges on the pivotal role played by cold dark matter. However, a lingering question has persisted. During the formation of galaxies in the early universe, Was it warm or cold dark matter that played a crucial role? Regrettably, discerning this difference in the local universe proves challenging. Thus, the quest for an answer to this question is confined to the first billion years of the universe, where the distinctive properties of warm and cold dark matter may hold the key to unraveling this cosmic mystery. The galaxies observed by the James Webb Space Telescope, with their significant redshifts, presented a unique opportunity to delve into the characteristics of dark matter and its role in shaping large-scale structures. In their research paper, the scientists initiated their investigation by plotting the star formation rate density against redshift. In the realms of galactic and extragalactic astronomy, the star formation rate holds considerable importance, serving as a metric for how rapidly stars emerge from gas and dust. This rate is typically measured in solar masses per year. The star formation density, in turn, signifies the star formation rate per unit volume. Redshift, a measure of distance, indicates the distance of a galaxy from us. Higher redshift values correspond to galaxies farther away. Upon plotting these parameters for the Webb-observed galaxies, researchers discerned a distinctive pattern. High redshift galaxies could only be elucidated by employing cold dark matter models. Contrarily, warm dark matter models failed to anticipate the formation of galaxies with high redshifts. Consequently, these models were discounted in relation to the star formation rate exhibited by the observed galaxies. Furthermore, the researchers conducted a comparative analysis of the mass distribution of these galaxies and the density of observed galaxies distributed across UV luminosity, scrutinizing the outcomes under various warm and cold dark matter models. The accumulated findings strongly suggest that cold dark matter remains a significant factor in the formation of galaxies in distant regions characterized by high redshifts. This affirmation aligns with our initial understanding of the dark matter's role in the creation of large-scale structures. However, a notable conundrum emerges for the Lambda Cold Dark Matter, LCDM model. While the LCDM model might accurately capture the essence of dark matter in high redshift galaxies, its projections regarding the intrinsic nature of these galaxies appear to be contradictory. Notably, properties such as elevated stellar mass, heightened star formation rates, and increased absolute UV magnitude do not align with the anticipations set forth by the most successful cosmological model to date. This discrepancy suggests a gap in our comprehension of the role played by dark matter during the formative stages of the universe, particularly within the first few 100 million years. It's crucial to emphasize that this contradiction in results doesn't negate the validity of the Big Bang Theory. The wealth of observational evidence supporting the Big Bang Theory remains intact. Any emerging theory aiming to elucidate the observations from the James Webb Space Telescope and the origins of the universe must harmonize with the well-established and validated predictions of the Big Bang Theory. These include key phenomena such as the cosmic microwave background, the abundance of chemical elements, and the redshift observed in distant galaxies. While attention is warranted across various aspects, a critical focus lies on enhancing our comprehension of dark matter. The James Webb Space Telescope's data signal a divergence from predicted patterns in galaxy formation, necessitating a re-evaluation and potential correction of these predictions. Such a correction could potentially unveil novel avenues for understanding galaxy formation and rectify potential flaws in our current understanding of gravity. Preserving the concept of dark matter remains paramount in this process, as its exclusion would destabilize the foundational structure of our most successful standard model of cosmology, the Lambda Cold Dark Matter, LCDM model. The ongoing debate surrounding the nature of dark matter carries substantial implications. Successfully addressing and rectifying our understanding of dark matter in the context of Webb's observations could preserve the integrity of the LCDM model, a culmination of decades of scientific development. Failure to reconcile these discrepancies may necessitate the formulation of an entirely new theoretical framework, potentially resetting our progress to square one. Do you think the LCDM model is correct, or is our understanding of cosmology about to change forever? Please share your thoughts in the comments below.